What if I told you that the chair you're sitting on, the screen you're watching this on, and even your hand right now don't exist in the way you think they do? Not as a metaphor, not as philosophy, but as a direct consequence of how the universe actually works at its most fundamental level. This isn't about perception or consciousness tricks. This is about what quantum mechanics reveals when we look closely enough at reality itself. And what it reveals is deeply uncomfortable. We spend our lives assuming the world is made of things, solid things, objects with definite properties, sitting in definite places, doing definite actions, whether we look at them or not. A rock is a rock. An electron is an electron. The moon is there even when no one's watching. This seems obvious. It's the foundation of everything we call common sense. But quantum mechanics systematically dismantles every single one of these assumptions, not through clever wordplay or philosophical speculation, but through rigorous mathematics and experimental results that have been verified thousands of times across a century of physics. Let's start with something simple, an electron. You probably imagine it as a tiny particle, a little ball of charge spinning somewhere in an atom. That's how we draw it. That's how we talk about it. But that's not what an electron is. When we're not measuring it, when we're not interacting with it, an electron doesn't have a position. It doesn't have a velocity. It doesn't even have a trajectory. These aren't things we fail to know about the electron. These are things the electron doesn't possess. The electron exists as something we call a wave function, which is a mathematical description of probability spread across space. It's not in multiple places at once, exactly. It's not in one place we haven't found yet. It simply doesn't have a definite location as a property of its existence. This sounds like semantic games until you realize what it means experimentally. Take the double slit experiment. Fire electrons one at a time at a barrier with two slits. Classical physics says each electron goes through one slit or the other. But when we look at where the electrons land on a screen behind the slits, we don't see two clumps matching the two slits. We see an interference pattern, the characteristic signature of waves overlapping and either reinforcing or canceling each other out. The only way to produce this pattern is if each individual electron somehow goes through both slits simultaneously and interferes with itself. Not that we don't know which slit it went through. The electron genuinely doesn't go through a definite slit until we force it to by measuring. And here's where it gets stranger. If you put a detector at the slits to see which one the electron goes through, the interference pattern disappears. The moment you measure which slit the electron passes through, it behaves like a particle going through one slit or the other, and you get two clumps on the screen instead of an interference pattern. The act of measurement doesn't just reveal a pre-existing fact about which slit the electron went through. The measurement creates that fact. Before measurement, there is no fact of the matter. The electron exists in what we call a superposition, a state where both possibilities are real components of its existence. This has been verified with photons, electrons, atoms, even molecules containing hundreds of atoms. It's not a quirk of tiny things we can ignore. It's how the universe works, and it leads directly to a question that sounds absurd but is completely serious. What counts as a measurement? What exactly forces the electron to pick a definite state instead of remaining in superposition? This is called the measurement problem, and despite a century of quantum mechanics, we still don't have a consensus answer. One interpretation, the most historically popular one, says that measurement collapses the wave function. The probabilities somehow become actualities when observed. But this raises immediate problems. What constitutes an observer? Does it have to be conscious? Does a detector count? Does a rock count? If you need consciousness, then you're saying consciousness plays a fundamental role in physical law, which seems bizarre. If you don't need consciousness, then where exactly does the line between quantum superposition and classical definiteness lie? No one knows. The math of quantum mechanics is extraordinarily precise and predictive, but interpreting what the math means about reality is where everything becomes murky. Another interpretation, the many worlds interpretation, takes the mathematics completely literally and says there is no collapse. When you measure which slit the electron went through, the universe splits into branches. In one branch, it went through the left slit. In another branch, it went through the right slit. Both outcomes are real, just in separate, non-interacting branches of reality. You don't experience the split because your consciousness goes along one branch only. This sounds like science fiction, but it's a serious interpretation that many physicists take seriously precisely because it doesn't add anything to the mathematics. It just accepts what the equations say way without inserting an unexplained collapse mechanism. There are other interpretations. Pilot wave theory says particles do have definite positions all along, but they're guided by a separate wave that evolves according to quantum rules. Relational quantum mechanics says properties only exist relative to interactions, not absolutely. Cubism treats the wave function as representing an observer's knowledge rather than objective reality. Each interpretation saves the mathematical predictions of quantum mechanics, but tells a radically different story about what's actually real, and crucially, they're empirically indistinguishable. We can't do an experiment to determine which interpretation is true because they all predict identical outcomes for every possible measurement we could make. So what does this mean? At minimum, it means that the properties we think objects have, things like position and momentum and spin, are not properties that exist independently of observation or interaction. They only become definite in contexts. If you're not interacting with something, it genuinely doesn't have those properties in any meaningful sense. Reality is contextual, not absolute. And if you take the many worlds interpretation seriously, it means there's no single history of events, no unique timeline where things definitely happened one way. There's a vast branching structure where all quantum possibilities are realized somewhere. But let's go deeper. Quantum mechanics also reveals something called entanglement, which Einstein famously called spooky action at a distance. When two particles become entangled, their properties become correlated in ways that can't be explained by them carrying predetermined information. You can separate entangled particles by any distance, light years if you want, and measuring one particle instantaneously affects the state of the other, not by sending a signal. That would violate relativity. But the measurement outcomes are correlated in ways that classical physics absolutely cannot produce. This was tested definitively by experiments confirming violations of Bell's inequality, a mathematical constraint that must hold if particles have definite properties independent of measurement and if no faster-than-light influences exist. The experiments violate Bell's inequality, which means at least one of those assumptions is false. Since we have strong reasons from relativity to believe no faster-than-light communication happens, the implication is that particles don't have definite properties until measured. The correlation exists in a way that transcends spatial separation. The two particles aren't separate objects with independent properties. They're components of a single quantum system whose properties are fundamentally non-local. This non-locality doesn't let you send information faster than light, so it doesn't violate relativity in a way that breaks causality, but it does mean that the universe isn't built from separate local objects. The fundamental level of reality is more like an interconnected web where separation is an emergent feature that only appears under certain conditions, not a foundational fact. Now here's where we need to distinguish carefully between what's established and what's speculative. Everything I've described so far, superposition, measurement problem, entanglement, non-locality, these are established features of quantum mechanics verified by countless experiments. The interpretations differ on what these features mean, but the features themselves aren't in dispute. What's speculative is extending these ideas to larger questions about the nature of reality as a whole. Some physicists and philosophers argue that quantum mechanics implies reality is fundamentally information theoretic rather than material, that the universe is better understood as a web of relationships and information processing than as objects moving through space. Others suggest that space and time themselves might be emergent from deeper quantum structures, that the geometry of space-time isn't fundamental, but arises from entanglement patterns in some more basic quantum substrate. These are active areas of research, particularly in quantum gravity and quantum information theory, but they're not yet established physics. They're promising directions with some theoretical support and some indirect evidence, but they remain hypotheses. What we can say with confidence is this: the classical picture of reality, where objects have definite properties, existing in definite places doing definite things independent of observation, is experimentally ruled out. It's not a matter of interpretation or philosophy. The experiments force us to abandon that picture. What replaces it is less clear. Maybe reality is fundamentally probabilistic and becomes definite through measurement collapse. Maybe it's deterministic but branching across many worlds. Maybe properties are relational and only exist between systems. Maybe consciousness plays a role. Maybe something else entirely that we haven't thought of yet. But all of these options share something crucial. They all reject the intuitive notion that reality is made of independently existing things with inherent properties. That notion, which feels so obvious and forms the basis of our everyday experience, is incompatible with quantum mechanics. So in that very specific sense, quantum mechanics proves that reality isn't real in the way we thought it was. This might sound like it's undermining the possibility of science or knowledge itself. If we can't trust that objects have definite properties, how can we know anything? But that's not the right conclusion. Quantum mechanics is itself a form of knowledge. It's extraordinarily precise knowledge that lets us build transistors and lasers and understand chemistry and predict atomic behavior with astonishing accuracy. What quantum mechanics reveals is that the world operates according to rules that are deeply counterintuitive but perfectly consistent and mathematically rigorous. The problem isn't that we can't know things. The problem is that what we know doesn't match our intuitions about how things should work. Our intuitions evolved to navigate a world of medium-sized objects moving at medium speeds, where quantum effects average out and classical behavior emerges. We never evolved intuitions for the quantum realm because our ancestors never needed them to survive. So when we probe that realm with careful experiments and mathematics, we shouldn't expect it to make intuitive sense. The surprise would be if it did. This raises a philosophical question that physics alone can't answer. If the fundamental level of reality operates according to quantum mechanics, and quantum mechanics is so different from our classical experience, then what exactly is the relationship between the quantum and the classical? Why do we experience a definite world even though the underlying reality is indefinite? This is called the emergence problem, and it's related to the measurement problem but broader. How does classical definiteness emerge from quantum indefiniteness? There are partial answers. Decoherence theory shows how interactions with the environment cause quantum superpositions to effectively collapse into classical-looking states for all practical purposes, even if they don't truly collapse in some fundamental sense. This explains why we don't see quantum weirdness in everyday life. But it doesn't fully solve the problem because decoherence itself is a quantum process. It explains why certain quantum states become practically inaccessible, but it doesn't explain why we experience one definite outcome rather than existing in superposition ourselves. Some argue this points toward a role for consciousness in collapsing the wave function, or at least in selecting which branch of the many worlds we experience. Others argue consciousness is itself an emergent phenomenon that arises from complex information processing in brains, which are ultimately quantum systems subject to the same rules as everything else. There's no scientific consensus here. Consciousness remains one of the deepest mysteries, and its relationship to quantum mechanics, if any, is unknown. What we're left with is a picture of reality that's radically different from common sense, but not arbitrary or mystical. Quantum mechanics is fully mathematical and predictive. It works. It's the most successful physical theory ever created by any metric you choose. And yet, interpreting what it means about the nature of reality leads to options that all sound bizarre in different ways. Either the universe branches into countless parallel realities with every quantum event, or some unexplained process collapses probabilities into actualities when measurements happen, or properties don't exist until systems interact. Or reality is somehow more information-like than substance-like at its core. Each of these interpretations has sophisticated advocates and technical challenges. None of them is obviously correct, and this ambiguity isn't because physicists are confused or haven't done the work. It's because the experimental evidence, as clear and compelling as it is, doesn't uniquely determine which interpretation is correct. The universe gives us the mathematical structure of quantum mechanics with extreme precision, but it doesn't tell us in any obvious way what that mathematics is describing. So where does this leave us? Practically speaking, quantum mechanics works perfectly for making predictions and building technology. Philosophically speaking, it forces us to confront the possibility that reality at its most fundamental level is nothing like we imagined. The objects and properties and definite states we rely on in everyday experience might be convenient approximations that emerge from something far stranger. This isn't a crisis. It's not a reason to give up on science or knowledge or rationality. If anything, it's a testament to how powerful scientific inquiry is. We've developed mathematical tools and experimental techniques precise enough to probe the foundations of reality, and we've discovered that those foundations don't conform to our intuitions. That's remarkable. It means we're not trapped by our intuitions. We can transcend them through careful reasoning and empirical testing. But it also means we live in a universe that's fundamentally mysterious in ways we're only beginning to appreciate. We have the equations, we have the predictions, we have the technology, but we don't fully understand what the equations are telling us about the nature of reality itself. And that's not a failure. That's the frontier. That's where the next century of physics might take us, toward a deeper understanding of what quantum mechanics is really describing and how it connects to the other great mystery, the structure of space-time and gravity. Maybe we'll discover that space and time are emergent from quantum entanglement. Maybe we'll find a unified theory that makes quantum mechanics and general relativity aspects of something more fundamental. Maybe we'll develop new experiments that finally distinguish between interpretations. Or maybe we'll realize the question itself needs to be reframed in ways we can't currently imagine. What's certain is this: the reality you take for granted, the solid, definite, independent world of objects and properties, is not the reality quantum mechanics describes. And quantum mechanics is not speculation. It's the most thoroughly tested and precisely confirmed theory in the history of science. So if you're looking for what's real, you have to confront the fact that real is stranger, more subtle, and more contextual than anything common sense prepared you for. That's not a comfortable conclusion, but it's an honest one. And it's an invitation to think more carefully about what we mean when we talk about reality at all. Maybe reality isn't a collection of things. Maybe it's a process, a pattern, a web of relationships that only looks like separate objects from certain perspectives. Maybe asking whether something is real or not is the wrong question, and we should be asking how it behaves, how it relates, what role it plays in the broader structure. These aren't just abstract philosophical musings. They're questions that matter for future physics, for understanding consciousness, for thinking about the nature of existence itself. Quantum mechanics opened the door to these questions by showing us that our intuitive picture of reality breaks down at the fundamental level. Where we go from here depends on continuing to follow the evidence wherever it leads, even when it leads somewhere uncomfortable. If this left you with more questions than answers, good. That means you're paying attention. Reality doesn't owe us comfort or clarity. It just is what it is. Our job is to understand it as best we can with the tools we have, while remaining humble about how much we still don't know. If that sounds worth exploring further, there's a lot more to discuss. Consider subscribing. The questions only get deeper from here.